In this FRQ, we have two spherical objects. Both of them are insulators. The first spherical object is this insulator here in the middle with the radius A. It has a positive charge Q, and its charge is uniformly distributed, meaning its density is the same throughout all points inside of the sphere. The other insulator is a hollow sphere with an outer radius of 3a and an inner radius of 2a, meaning that this part inside of the shell has a radius of a. This shell has a charge of negative q, which is also uniformly distributed within the shell. The first question is asking to use Gauss's law to determine the magnitude of the electric field based on the different positions of R based on 4 different regions. It's going to ask for the electric field if R is less than A, if R is less than 2A but greater than A, if R is less than 3A but greater than 2A, or if R is greater than 3A. And for all of these problems, we can use Gauss's law. So if we go over here and we start with the first one, first we want to determine, before we do any Gauss's law problems, we have to determine which Gaussian surface we want to use. There's 3 surfaces that are typically used. There is the pillbox, which looks something like this. This is used for when we have a sheet, a charged sheet typically, and we use this area on top, this flat area. There's another one, this cylinder. We would use this Gaussian surface for a long thin rod, or any type of long cylindrical rod, and we would use this round area for the Gaussian surface. But in this case, whenever we have a spherical object, a spherically charged object, or if we have a point charge, since this spherical object has a radial electric field, we're going to use a sphere, because a sphere can perpendicularly have electric field pass through it. So in this case, we're going to use a sphere for that Gaussian surface when the R is less than A. So we would draw a Gaussian surface something like this inside of the first spherical shell. Now we would use first we would write down Gauss's law, which is given by flux equals to the integral of E dA, which equals to charge enclosed over epsilon naught, which is permittivity of free space, which is a constant. When we have something like this, we can simplify this down to E times A, where E is the electric field directly outside the Gaussian surface, or the electric field that passes outside the Gaussian surface, and A is the surface area of our Gaussian surface. And Q enclosed is the charge inside of our Gaussian surface, which we will get to later. And this is obviously a constant. This can boil down to E times A, just using integral calculus. So we have this sort of setup that we're going to use for all 4 sections of this problem. So first we can find out A pretty easily. The area of our Gaussian surface has a radius r. The surface area of a sphere is 4 pi r squared. Q enclosed is a little harder to figure out, but it becomes easier once we realize that our density is the same throughout the entire sphere. So we can say that this plus q, this charge over this entire sphere has the same density. So d equals plus q over charge divided by its volume, which is 4 over 3 pi, and the radius is a, pi a cubed, which will also equal the density of our Gaussian surface, the charge inside. So it would be q enclosed, which is what we're trying to solve for, divided by the volume of this Gaussian surface, which is using r instead of a. Now we can just, all we have to do now, isolate the q enclosed. We can multiply both sides by 4 pi r cubed, and if we do that, these two 4 over 3 pi will cancel out, so q enclosed becomes r cubed over a cubed. So now all we have to do pretty much is just plug it in and isolate e, and then we'll have our answer. So I'll just e times a, which is up here, r squared, equals to this is wrong. I meant to put plus q because this q enclosed equals that. And then we plug in q enclosed, which is this. So q r cubed over a cubed. But then remember we have the epsilon naught. And now all we have to do is divide by 4 pi r squared. So e equals q r cubed over a cubed epsilon naught 4 pi r squared, and then this will equal to, this will cancel out, this will become a 1, and then we also have, we can remember that k equals 1 over 4 pi epsilon naught. This is the Coulomb's constant, and so we pretty much have that here, so we can just multiply k q r, divide that by a cubed, and this is our final answer. So I'll just write e equals, and this is the magnitude, by the way, kqr r over a cubed. And so that was the first section. Now for the second section, when r is less than 2a, greater than a, but less than 2a, we will use the same sort of deal, same equation, except our Gaussian surface is going to be around here, obviously using a sphere again, and this time we'll write the radius as this. Now we can boil this down to e times a. We can skip that by just writing 4 pi r squared. And now this q enclosed is not as complicated, because as we can see, this Gaussian surface, the charge enclosed by that surface is just plus q. That's all that's inside there. This white space over here has no charge, so we can just replace that with q epsilon naught, and then we can say e equals q epsilon naught 4 pi over r squared, and then as we said before, k equals 1 over epsilon naught 4 pi, so we can rewrite this as kq over r squared. Then that's basically our answer. One thing to note, this answer looks like the same equation for E from a point charge that's on the formula sheet, which is just KQ over R squared. The reason this comes out to be that is this concept that when you have an insulator or a sphere, such as this one, as soon as we get outside of that sphere, the entire charge, or this entire sphere, all this charge and all the electric field coming from it can be boiled down to, it can be mimicked by a point charge. So the electric field based off this sphere, when we're in this space over here, is the same as the electric field as if we had a plus Q. So that's just a little hint that comes in use later. So this answer is E equals KQ over R squared. Now we can do when A is, or when R is greater than 2A but less than 3A, meaning our Gaussian surface is in the shell over here. If I can, there. And then obviously we're going to have the radius of R. We will write down every time we do this equals Q enclosed over epsilon naught E times 4 pi R squared surface area equals Q enclosed. Now we have to find out Q enclosed. This is going to be a lot more difficult because we have not only the charge plus Q that's stored in here, but we have this sliver of charge from the shell, which we're going to have to solve for here. So I'll just write Q enclosed equals plus Q. And then for this sliver of charge that is encapsulated from the shell, I will call that Q, little q. So plus little q. Now we have to solve for little q. And to find q, we can use the same concept from earlier about uniform charge density. So we can say negative q, charge of the whole shell, divide by the volume of the shell, which we can get by 4 over 3 pi 3a cubed minus the hollowness, this hollow space over here, which isn't included in the volume, so we have to subtract from it, over 4 over 3 pi 2a cubed, and this cubed is on the outside, cubed, and then we can set that equal to q over, we can do this, 4 over 3 r pi r cubed minus the hollow part, because we're only looking for this volume, minus 4 over 3 pi 2a cubed. And so basically this, well, we're gonna multiply, so this part cancels out, this part cancels out, all the 4 over 3 pi's cancel out, and what we have left is negative q times r cubed minus 8a cubed over 27a cubed. Oh, this is 27a cubed minus 8a cubed, which is just 19a cubed. And yeah, we can plug that into here. So q enclosed equals plus q, and then plug this in, minus q, because this equals q, minus q r cubed, there's parentheses here, r cubed minus 8a cubed over 19a cubed. We can also factor this a little bit. But basically, you don't actually need to do all this work. I don't think you need to simplify it as much. But yeah, we just plug this into here. So this equals to Q encloses this. I'll divide now 4 pi r squared, and then I forgot about this chunk. So this is 27 over 19 minus r cubed over 19a cubed, and this can be written as k, so but I'm not going to write all of that. This should suffice as a final answer, so I'm just gonna do that. I'll do this. Then the fourth part of our is gonna ask about when the r is greater than 3a. Now, just from looking at this, well, we'll just do it the Gaussian way. So basically, we can write all this stuff, whatever, over EA equals Q enclosed over EA. Okay, so basically, when we look at this, the Gaussian surface is going to be something like this. This Q enclosed over here, the charge enclosed by this Gaussian surface is plus Q minus Q. So this equals 0, meaning E times A equals 0. And this area is a number, so this E must be the 0. So we can just say E equals 0. That's the final answer for this question. And then we can move on to the next ones. Okay, part B says, what is the electrical potential at the outer surface of the spherical shell R equals 3A? And explain your reasoning. So basically, if we want to find the electric potential right here, we can use the fact that infinitely far away from this charge, V equals 0, right? So we can say voltage from the outside, 3A, minus the voltage from infinity equals negative 3A infinity, this integral E times dr, we're going from infinity to 3A. That's going to give us the voltage, this difference over here. And we know that this equals 0. Okay, so all we need to do, 3A minus 0, we use what we know. And what we also know, other than the fact that the voltage, potential at infinity is 0, the electric field outside of 3A is also equal to 0. And because this value over here is 0, this whole integral becomes 0. So V3A just equals 0. That's our answer, and this is our explanation for it. Part C says derive an expression for the electric potential Vx minus Vy. We can use something very similar to this to find the difference between x and y here and here. So we can just say V, or difference V, equals Vx minus Vy, which will equal to negative the radius at x. What's the radius at x? It's A. What's the radius at y? It's 2A. So we're going from 2A to A. And then electric field times dr. The electric field we have from a previous answer right here is just kq over r squared. So this will equal negative A 2a of kq over r squared dr. We can take out some stuff. These two are constants, so negative k q a 2a 1 over r, or we can just say r negative 2 dr. So this will integrate to negative 1 over r. Okay, and so we just multiply this by the integral of this. These negatives will cancel out, so we should just have kq over r, and then we'll have from 2a to a, and so this will equal kq over a minus kq over 2a. We can factor out kq, 1 over a minus 1 over 2a, and I think that's the right answer.